Welcome to the second part of Unit 13. In this part, we are going to be talking about a particular type of collision called an inelastic collision. Remember in the last part, I mentioned that momentum is particularly well set up for dealing with the interaction of objects. And one of the easiest ways that objects can interact is by colliding into each other. To begin with, we're going to look at this simulation, which I've already pulled up here. I'm going to click more data because it shows numbers really quick. And what I want you to focus on is the momentum. So right now, the red ball 1 has a momentum of 0.5 kilogram meters per second. And the green one has no momentum because its velocity is 0. And when I hit play and have them interact, they are now both moving. And the momentum of the red one is negative 0.25 kilogram meters per second, whereas the green one is 0.5. Has a velocity of 0.5 meters per second, which makes a momentum of 0.75, and the total momentum is still 0.5 kilogram meters per second. Now, I'm going to reset this. Back it goes. Exact same starting conditions that we had before, but I'm going to come up here and change this slider. So notice the first one had an elasticity of 100%. And now I'm just going to change it, bring it down to, I don't know, let's try 75. And make it go. And so now we have a different set of final velocities and a different set of final momentums, but if you add them together again, we still get 0.5 kilogram meters per second. Restart again, bring the elasticity down a little bit more. We'll aim for about 50. There we go. Tell it to go. And here we have a third set of final velocities and momentums still add up to 0.5 kilogram meters per second. And we're going to do 2 more of these. I forgot to restart it, but that's okay. We'll make it go now. So now something different has happened. Instead of the red ball rebounding and heading back the way it came, it is now moving still in the direction in which it started, but the total momentum still is 0.5 kilogram meters per second. And lastly, bring it all the way down, make it go. And on this one, they stick together. So the final velocities are the same, and the final momentums still add up to 0.5 within a little bit of round off error here. Okay, what I'm varying, you can see it says elasticity 0%, is I'm changing how much energy is conserved as these two collide. So if I look at kinetic energy and restart with my inelastic collision or completely inelastic collision, I go from 0.25 joules to 0.06. And if I go back all the way to 100%, I start with 0.25 joules and I end with 0.25 joules. And everything in between conserves a different amount of energy. What you will find is that there is one particular set of final velocities that perfectly conserve energy, and that results in a set of collisions known as elastic collisions. Every other collision loses energy to some degree, and the one that loses energy the most is known as a completely inelastic collision, and that is when the two objects stick together. So returning to our PowerPoint file, summarizing this, elastic collisions conserve kinetic energy and momentum. Inelastic conserve only momentum. Okay, so that's the difference. in this particular unit, we are going to be focusing on this category of inelastic collisions. Color it in a little bit. And for our first one, we're going to begin with a completely inelastic collision involving a railroad car. So we have a 12,600 kilogram railroad car traveling, that shouldn't be alone, it should be along, sorry for the typo, along a frictionless track at a constant speed of 18 meters per second. A 5,350 kilogram load initially at rest is dropped into the car, and then the car with its load moves off. And we want to know how fast does it move off and is energy conserved. We already know that energy is not going to be conserved for this because this is a case of they move off together. It's a completely inelastic collision. But instead, let's check how little energy is conserved. When working conservation of momentum problems, the first thing you should do is draw a picture. So here's my initial situation. I have my railroad car moving and my load, whatever it is. So V initial car, V initial load, but that one is 0 meters per second. And now I can write the initial momentum after I define my positive direction, which makes sense to make it in the direction of velocity, so that's what I'm going with. That's going to be the mass of the car times V initial car plus the mass of the load, V initial load. The mass of the car was given to be 12,600 kilograms and the initial velocity of the car at 18 meters per second. The mass of the load was 5,350 kilograms and the initial velocity of the load was 0. So if you multiply all of that together, you get 226,800 kilogram meters per second. And now we draw a second picture for what is happening after. For this, you want to keep your positive direction the same, so I'm going to stick with to the right. Here is my load sitting in the car, and it's got some velocity which we don't know. So our final velocity, there's two ways you could write this. I will show you both, if you will. So we have the mass of the car, the final velocity of the car, plus the mass of the load, final velocity of the load. But remember, the final velocities are the same because they move off together. So one way I could write this is by each term separate, as I've done in the first two lines. The other way I could write it is saying, hey, these two things are moving together, therefore I can just add their masses together. When I add the two masses together, 12,600 plus 5,350 gives me 17,950 kilograms times V final. And now I can say momentum must be conserved. So the initial momentum has to equal the final momentum. Remember, the initial momentum that I found was 226,800 kilogram meters per second. And that equals 17,950 kilograms times V final, which gives me V final equaling 12.635 meters per second. It is positive, so that tells me to the right. So that answers the first part of this problem. The second part is wondering, is energy conserved? I thought I had another slide there and I don't, so we'll just do it here. So our initial energy, there's an arrow over energy. Energy is not a vector. Is going to be 1/2 times the mass of the car, V initial car squared, plus 1/2 mass of the load, V initial load squared. So that's 1/2 of 12,600 kilograms times 18 meters per second squared plus 1/2 5,350 kilograms times 0 meters per second squared. And when you multiply all of that out, you get 2,041,200 joules. I'm going to take option 2 and combine my masses for the final energy because they do move at the same velocity. So that's 1/2 of 17. Did I say it was 17,950? Yes. And the velocity was 12.635 meters per second squared. And that results in an energy of 1,432,798 joules. And we see indeed that our initial energy does not equal the final energy, therefore it is not conserved. For the next example, we're going to be dealing with two air hockey pucks colliding. Before the collision, the 0.2 kilogram puck is moving at 1 meter per second to the right, and the 0.3 kilogram puck is moving at 0.5 meters per second to the left. After the collision, the 0.2 kilogram puck is moving at 0.48 meters per second to the left. So I'm going to begin by drawing the two pictures. So the initial picture looks like this. We have the 0.3 kilogram puck, 0.2 kilogram puck moving at 1 meter per second to the right, and the 0.3 kilogram puck moving at 0.5 meters per second to the left. After the collision, the 0.2 kilogram puck is moving, try fixing that arrow a little bit here. The 0.2 kilogram puck is moving to the left at 0.48 meters per second. And we don't know what the final, oh goodness, that's not supposed to be an arrow, final velocity of the 0.3 kilogram puck is. Okay. But using conservation of momentum, we can find it. So I'm going to begin by writing out that the initial momentum is going to be the momentum of the 0.2 kilogram puck. If I define to the right as positive, then that momentum is going to be 0.2 kilograms times a positive 1 meter per second. Going to add to it the momentum of the 0.3 kilogram puck, so that's 0.3 kilograms times a negative 0.5 meters per second. It's negative because it's going to the left. And if you multiply all that out, you get 0.05 kilogram meters per second. The final momentum of the 0.2 kilogram puck is 0.2 kilograms times a negative 0.48 meters per second. And it's negative again because it's going to the left, and we've defined to the right as positive. Plus the 0.3 kilogram puck times the unknown final velocity of that puck. We can now use conservation of momentum, stating that the initial momentum equals the final momentum. So 0.05 kilogram meters per second equals, I didn't multiply it out on the right previous page, so I won't multiply it here yet either. Okay. So 0.2 times negative 0.48 is negative 0.096 kilogram meters per second plus 0.3 kilograms times V final. Moving the 0.096 to the other side results in 0.14, that's a 46 kilogram meters per second equals 0.3 kilograms times V final. Or in other words, V final is 0.049 meters per second. And we note that, hey, it's positive, which means this puck is moving to the right, because positive in our coordinate system was to the right. Next, we can check if energy is conserved. So the initial energy of the system will be 1/2 times 0.2 kilograms times 1 meter per second squared, plus 1/2 times 0.3 kilograms times 0.5 meters per second squared, and that equals 0.1375 joules. The final energy is 1/2 times 0.2 kilograms times 0.48 meters per second squared, plus 1/2 times 0.3 kilograms times 0.49 meters per second squared, and that equals 0.059 joules. We see again that the initial energy does not equal the final energy. Therefore, there's a does not equal there. Energy is not conserved. Lastly, I forgot about the explosion on my earlier slide. So, an explosion is a perfectly inelastic collision in reverse. So remember, with a perfectly inelastic collision, you have two things that start doing something else, but then after the collision, they're moving together. With an explosion, the objects start moving together and then they split apart and do something else. So it's a perfectly inelastic collision in reverse. Here we have a 5 kilogram object traveling at 300 meters per second through space. It splits into two unequal pieces. Afterwards, the 3 kilogram part is traveling at 100 meters per second in the opposite direction. And we want to know how fast is the remaining 2 kilogram part moving. So our initial situation looks like, here's my object, whatever it is. I have a 3 kilogram part and a 2 kilogram part, and they are both moving at 300 meters per second through space. I'm going to let that direction determine my positive direction. After the collision, make sure I get this right this time, the 3 kilogram part is moving at 100 meters per second in the opposite direction. And the question is, what's the final velocity of the 2 kilogram part? So the initial momentum is the mass of the 3 kilogram times the initial velocity of the 3 kilogram plus the mass of the 2 kilogram times the initial velocity. That F was supposed to be a 3 of the 2 kilogram. So that's 3 kilograms times, what did I say, 300 meters per second plus 2 kilograms times 300 meters per second. And if you do all that up, that turns out to be 1,500 kilogram meter per second. Final momentum is the mass of the 3 kilogram times V final 3 plus the mass of the 2 kilogram V final 2, which is 3 kilograms times negative 100 meters per second plus 2 kilograms times the unknown final velocity of that portion, which equals negative 300 kilogram meters per second plus 2 kilograms times V final 2. I can equate the initial momentum to the final momentum. So 1,500 kilogram meters per second has to equal negative 300 kilogram meters per second plus 2 kilograms V final 2. So 2 kilograms times V final 2 has to equal 1,800 kilogram meters per second. Or in other words, V final 2 is 900 meters per second, and it is positive, so therefore it's going now in the original direction. And going that way quite fast. This concludes this part of Unit 13. In the next part, we're going to focus on elastic collisions.